anyone has heard anything about thermodynamics. Yeah, no, there is no big issue there. We will not need it for the lecture anyway. But if you're interested how to derive the isentropic speed of sound, then you can just look it up there. Thermodynamics in general aims to describe states of control volume by different energy functions. There are different energy functions which are defined in the field of thermodynamics, and using these energy functions you can derive general statements for state variables. So imagine a control volume has a defined state, and based on the assumptions we use, for instance, we heard last week this isentropic, homotropic, and adiabatic state, and based on this state you can then define the connection of state variables, and considering one of these restrictions like adiabatic or stuff like that, there is a relation how many degrees of freedom you more or less have. So for instance, when we have here the thermodynamic equilibrium and a homogeneous fluid, then two intrinsic state variables determine the state of the fluid. This means more or less this holds for acoustics in the thermodynamic equilibrium. Then we can relate two intrinsic state variables by a kind of this equation, so that a change in the pressure depends on two other state variables. State variables are the density and the entropy. And this relation always has kind of the, looks like this. If we are in the isentropic case, then we can define the isentropic speed of sound. It's more or less defined like this. So here we have the isentropic speed of sound, and comparing it to that, the isentropic speed of sound is more or less derivative with respect to the isentropic state, and then you have more or less the material parameter, which is now the speed of sound. This means, starting from thermodynamics, you can define the acoustic state being isentropic, and then you arrive at this equation, and you can use it then further for your wave model. And you can then derive the wave equation and stuff like that. So it starts like this. You're aiming for a wave equation, and then at some point you're ending up at the conservation of mass and the conservation of momentum. And you don't know how to connect the pressure and the density. And then you start thinking about how can I connect them? Okay, probably we assume thermodynamic equilibrium and it's not very restrictive. And then, okay, probably also it's a reversible process and it's adiabatic, so we have no heat transfer. Then we can think, probably also the isentropic case, as we stated here, is a valid assumption. And with these assumptions, we then can say, okay, the pressure is related to the density, with this equation, and then inserting this equation in the conservation of mass and conservation of momentum, then we can derive indeed the wave equation. So this is more or less the process how it works. And physicists did, I think, about 200 years ago. And then they arrived at the wave equation, and that was basically the whole story about how they came up with the wave equation and how the concept is different from on the one side seeing what's a physical or what's a property of just the kinetics, and then what's a property of the relation between different states and how the material comes into the play. Okay, I think it was described very complicated. Long story simple. The acoustic pressure relates to the acoustic density with the isentropic speed of sound squared. That's the message you should take. If you're faced somewhere or somehow in the future with some different material laws, either just contact us or have a look at the slides and the basic concept, how you come up with that. Okay, then the next thing we will discuss is the Newtonian fluid. Hopefully it comes on the next slide. Oh, probably not. The Newtonian fluid, I will just sketch that here. The Newtonian fluid aims to connect shear stresses with the gradients of the velocity in a spatial direction. I just say it here with the x-coordinate. Just imagine that we have a kind of a shear stress and it's connected to the velocity gradient somehow, and it's connected by just a scalar coefficient, which is the viscosity. And that's basically the concept of the Newtonian fluid. The thing or the question is, why do we have this? Probably going back to the conservation equations we had here, going to the incompressible state, we had here the velocities. Okay, velocities are unknowns. So this equation is a scalar equation, and it means that we can obtain with this equation one unknown. But as we have here the velocity, we have already 3 unknowns, so we have 1 equation and 3 unknowns. This is more or less bookkeeping what I'm doing now. And then in the incompressible state, we have here then another 3 equations, and we introduced in the incompressible state we have the density doesn't matter. We have here another unknown, so another unknown, and here we also have the stresses as I illustrated before. These are another 6 unknowns. This means we have 4 equations, and we already have now 10 unknowns. Not very good. This is why we come up with this model here, and this relates this to the velocities, and this means we have now 4 equations and more or less only 4 unknowns, because it's already related by this constitutive equation, and now we are fine and can solve we can solve this. Okay, that's basically it from the Newtonian fluid. And if we solve the conservation of momentum and using a Newtonian fluid, we have the famous Navier-Stokes equations. So probably just to keep in mind, Navier-Stokes equations are conservation equation plus a Newtonian fluid. These are already solvable. Nevertheless, there are some issues, and we will cover them now. Okay.
I'm sorry.
Okay.
Can you just briefly explain what does thermodynamic equilibrium mean?
What this means? Very short. It means more or less a lot. I'm not 100% sure what type of assumptions all go into the thermodynamic equilibrium, but it means that in a pragmatic way, it means that you have no matter that it is reacting. You have no change in the basically, first of all, you have no reactions in the material, so that the material properties itself will change, so that these coefficients are more or less determined. This is basically it. So for instance, you have a kind of inert gas, then you can assume thermodynamic equilibrium. It's also about if you have very strong gradients in terms of expansions or stuff like that, this will be definitely not in thermodynamic equilibrium. So you have some transients going on. So that's basically a pragmatic description of the thermodynamic equilibrium.
Okay, thank you.
But for any details, you must probably look it up in a thermodynamics book.
Okay, thank you.
Okay, probably a question mark there. Okay, so we have probably 2 to 3 minutes left, and yeah, we go again to the dimensionless numbers, and then that was it for the lecture. Dimensionless numbers. You all know the Mach number. Probably then we start with the Mach number. The Mach number, you can separate flow situations in compressible and incompressible range. Basically for Mach smaller than 0.3, we say, okay, we do an incompressible flow simulation, keep it simple, and all is good. Yeah. So Mach number helps you to decide what type of flow simulation you're doing. Then going on with the Reynolds number. Is viscosity negligible? So probably all of you know the Euler equations. Okay, so very high Reynolds number says that you are in the Euler regime. I think so. So okay, neglecting viscosity means that you end up with the Euler equations. Not neglecting viscosity, you have either laminar or turbulent flow. Anyone knows what's a laminar flow? Probably.
A flow without vortex, more or less.
It's a flow without turbulence scales. So the flow can have a large vortex, but small vortices are not there. So you have no small vortices that are granular in a turbulent sense. This means in the spectra, So if you have a kinetic energy spectra over a frequency, this big discrete vortex will look like a large peak. And then the turbulence is more or less a broadband component. And the broadband turbulence we are not resolving by laminar flow, but with a turbulent flow model, we either model the turbulent broadband behavior or we resolve it directly. But resolving directly is kind of a hell. So it's a big computational burden. Okay, and I think these three numbers are, yeah, I will make a homework for you. Just look them up, what they are. So the Struhel number is more or less a dimensionless flow frequency. The Helmholtz number is related to acoustics, and you can decide having compact acoustics or not. I think most of you know the Helmholtz number. And then we already had the Knudsen number, which is able to decide if we are in the continuum theory or not. So please look these three numbers up in the lecture notes. And yeah, I think that's it for today. Any questions? We have 2 minutes left.
Can I ask a short question?
Yeah, of course.
About the laminar flow and turbulent flow and the Reynolds numbers? I looked some things up, and what is a high Reynolds number? Is it a Reynolds number with 10 to the power of 6 and 7, or how can I? Yeah.
Okay.
What is a high Reynolds number? Because in literature, when you look it up, there are different opinions, more or less.
Just as a small sketch, we have Reynolds numbers 0 to Reynolds number whatever, and then there is it's called Reynolds number critical. Reynolds number critical. Below we say that we have laminar flow, and above we say we should use a turbulence model. It depends on the case, so on the setting of the domain. But for instance, for the cylinder, it should be about 500. It's not precise. It really depends on the setup. Probably it's also 2000, but it doesn't really matter. There is a critical Reynolds number. Below you can use a laminar model. Above you can or you should use turbulence, a turbulent model to describe it. This transition here is kind of fuzzy. There is no precise definition. So it's a kind of a transition zone. Okay, you're fine with that?
Yeah, thank you.
Okay, perfect. For any other questions, please ask them next week. We have the last lecture on fluid dynamics next week, and we start at 8:30, and it's a normal lecture from 8:30 to 10 a.m. Okay, then I wish you a nice week, and have a happy exercise with Paul, and we will see us next week. Goodbye.
Bye bye. Thank you.